All right, welcome everybody. Happy to be here and thanks for joining. So, while we wait a minute to start the presentation, I'll briefly introduce our speakers for today. Today we have two speakers. The first one will be Alessandro Battaglia, who is an associate professor in the Department of Environment, Land and Infrastructure Engineering at Politecnico di Torino in Italy. He has a master and a PhD in physics, and he's experienced in microwave remote sensing of clouds and precipitation, particularly in spaceborne Doppler radars. He's a member of the NASA Precipitation Measuring Mission Science Team and of the INCUS team. He's also a member of the ESA-JAXA Quality Working Group of Earth Care and of the ESA Mission Advisory Group of WIVERN. Indeed, today's presentation will be about WIVERN, which was selected as the 11th Earth Explorer mission. Our second speaker is Louis Marié. He's an experienced seagoing oceanographer with a strong background in the physics of turbulent flows. He works at Ifremer in France, and he's also part of the Mission Advisory Group, if I got it right, where he brings his expertise in oceanography and Earth interactions. So I think without further ado, Alessandro, the floor is yours.
Thank you very much, Agostino. Thank you for the introduction and thank you for the invitation to this webinar series. So today, hopefully I can advance the slides. Myself and Louis will try to introduce to you WIVERN, which is an acronym for Wind Velocity Radar Nephoscope. Is now the Earth Explorer 11 mission. So the Earth Explorers, are the pioneering scientific and technical missions in the Earth Explorer program. And essentially the mission, after a very long and competitive selection process, was finally funded and finally accepted as the Earth Explorer 11 in September last year. And WIVERN will now enter phase B studies. We should start basically in the next weeks. The expected launch of the mission is 2034, and the duration of the mission is for more than 8 years. So today, what I want to do is to briefly introduce the science underpinning WIVERN. I want to describe the WIVERN instrument, highlighting what this instrument will measure and which product will be retrieved. And I will also use tropical cyclones as an example to demonstrate the capabilities of the mission for enabling science. So in my part, I will mainly focus on the atmospheric component, and then Louis will try to discuss a little bit about the potential of WIVERN in characterizing the ocean by looking at the surface backscattering and the Doppler frequency shift. Okay, so well, typically to explain the science of WIVERN, we show this picture. Of course, if you observe our planet from space, we immediately see that Earth is stormy. And storms are complex and diverse. Here you can see tropical cyclones, mesoscale convective systems.
Sorry, Alessandro. We still see
Yes?
the timeline. We still see the time. Okay, there you go.
Okay, yes, sorry.
We have it.
I think there is a little bit of delay going on. Okay, sorry. Maybe
that's okay.
The connection is not okay. Anyhow, so I was saying Earth from space is stormy. Storms are complex and diverse. You see many different kind of storms, ranging from extratropical cyclones, polar lows to typhoons and hurricanes. And essentially, storms actually shape the weather. because they transport heat, they transport momentum, they transport moisture around the planet. They also bring the majority of precipitation across Earth. And they also connect dynamics across scales from the convective to the essentially to the synoptic scale, and also with their clouds, they are of course at the heart of the cloud radiative feedbacks. And last but not least, they are also associated to extreme events like windstorms, floods, and hailstorms. So very important component of our climate system. So what are WIVERN science goals, the primary ones, and then we will cover the secondary ones. Well, the first one is to deepen our understanding of storm dynamics by quantifying the strength, the structure, and the horizontal extent of internal circulation in storms. And particularly, we want to understand the role of played by in-storm horizontal mesoscale circulation and vertical wind shear, because these are key drivers of the organization and intensification of storms. And WIVERN will also somehow unveil the nexus that there is between the storm three-dimensional mass, of condensates, and the latent heat structure and the internal circulation of the storm itself. The second goal is constraining cloud and precipitation feedbacks on climate. And particularly, we have three foci. The first is on ambient cloud feedbacks. The second is in the measurements of precipitation and shallow precipitation over the ocean. And this is particularly being enabled by the fact that we have a radar radiometric mode at a sub-kilometer scale resolution. And then also we want to focus at high latitude snowfall. The third science goal, on the other hand, is to provide and improve numerical weather prediction via data simulation, be it traditional or artificial intelligence driven, and to benchmark Earth system models across regional domains and on seasonal scales. And we are confident to do this because of the very good sampling that WIVERN will have. And in particular, we think we will be able to do a very good job, particularly for what we call the glaciated part, so the part of the clouds that are above the freezing level. So how do we fulfill these goals? Well, if you think about it, storms all share a common features. Air moves vertically and horizontally within storms, and it is this movement of the air that drives the formation of clouds and precipitation. So what is the current situation in terms of the observing system trying to look at the movement of air in our atmosphere? Well, in the current observing system, we observe winds at the surface for sure, for instance, with SAR or with scatterometers, in clear air with LiDAR, for instance, EURUS has demonstrated that, at the top of the clouds via geostationary observation, but none of the current or planned observing system, except WIVERN now, provide global profiles of in-cloud winds, so winds inside storms. So WIVERN will be the first mission which will fill this observational gap. So how are we going to do this? Well, we have a unique single instrument payload, a 94 gigahertz, so 3 millimeter wavelengths W-band conically scanning Doppler radar, looking at a slant angle of 42 degrees. And this radar will provide an 800 kilometers worth. Thanks to the large dish, roughly 3 meters, the vertical resolution will be about 600 meters, and the horizontal less than a kilometer. Just to, if you have a radar expert, the other important parameter is sensitivity. We'll have a sensitivity about around minus 23 dBz at 1 kilometer integration. And the satellite will fly on a polar satellite with a sun-synchronous orbit. And basically, we will have roughly, on average, a 1.5 day revisit time. Of course, it will depend on the latitude. Now, just to give you a better idea about the WIVERN acquisition and the products, level 1 and level 2 products that we envisage, I will now try to use what we call an end-to-end simulator that actually we have performed here at Politecnico di Torino of one of the most iconic type of storms, a hurricane. And in particular, we use a snapshot of Hurricane Milton, which was the most intense hurricane in 2024. The hurricane has been simulated with WRF, and the snapshot corresponds to the 7th of October, 2024, when Milton was a Category 4 hurricane in the middle of the Gulf of Mexico. So hopefully you now see the video that I play. And the first thing, and the first thing I show are
we still see the, sorry, Alessandro, we still see the slide.
Okay.
The previous slide.
No, I think it's okay.
Okay.
Oh,
so
it's probably me.
So, okay, so I'll start with the model output. So this is the model output, so the three-dimensional hydrometer mass content. You can clearly see the features, the characteristic features of a hurricane, the eye wall, and the spiraling bands. So the system you see is 600 kilometers wide and 16 kilometers tall. So to better visualize the vertical structure, now what I show are horizontal cross-section of the hydrometer contents at different heights, going from 14 to 1 kilometer. And the image with white and blue colors is the vertically integrated hydrometer content that I leave as a reference. And now you see I'm simulating a descending orbit of WIVERN over the hurricane with a ground track passing, you see, east of the eye. You see the antenna performing the conically acquisition over the 800 kilometers worth. Basically, after 40 rotation, WIVERN will provide a complete mapping of the hurricane three-dimensional structure. And you think about this has been done in less than 2 minutes. So now level 1, range resolve radar reflectivity, this is what I'm showing, are basically proportional to the backscatter power, and they are basically a direct indication of the condensed mass. Above the freezing level, for instance, in this case, the freezing level is around 5 kilometers, this radar reflectivity can be converted directly into ice water content via typical Z ice water content relationship. And the ice water content will be one of our level 2 products. Now, what I'm doing now, I'm showing the circulation of the hurricane. So this is the model output again. You can clearly see the structure of the winds going again from the top of the hurricane to the lower troposphere. And clearly you see the strong cyclonic circulation around the eye here with winds reaching 50 meters per second. Again, I leave this as a reference for now showing the overpass of WIVERN. And this is the acquisition, again, of what we call the level 1 line of sight Doppler velocity. You see winds going from minus 40 to 40 meters per second, which is actually the unambiguous range velocity, sorry, the unambiguous velocity for WIVERN. And again, as the antenna turns around, you see the wind velocity component, which is measured along, of course, the antenna bore site. Again, you can see WIVERN sampling multiple slanted cuts through the hurricane. It looks like a waffle acquisition. And these measurements in the stratiform region can be converted into what we call horizontal projected line of sight winds, which will be our flagship level 2 product. And this will be the product that will be used directly into data simulation. And actually, I will not show that, but Meteo France has demonstrated that assimilating this product will give great benefit to data simulation, they think and they forecast an improvement as good as what EULOS 2 has already demonstrated. So I hope that the video gave you the idea about the WIVERN potential for vertically resolving simultaneously dynamic, so the winds, and mass, so the hydrometer mass contents. And the other important thing is that WIVERN is bridging between the kilometer scale, its footprint, to the mesoscale, okay, so, let's say 800 kilometers. And remember that for a big storm like a hurricane, we have essentially a full snapshot of the storm, a full three-dimensional snapshot of the storm, of course with gaps, with sampling gaps, but in less than 2 minutes. Okay, now I want to give you a little bit an idea about the products we are actually starting producing the machine for, let's say. So from the actual raw measurements, let's say, which are the radar reflectivity, the line of sight Doppler velocity, and also the brightness temperature. We have also a radiometric mode that will measure brightness temperature at 94 gigahertz with exactly the same antenna that we are using for the radar. From this level 1B products, we will basically generate wind products. And wind products essentially will be horizontal line of sights, wind velocities. This will be mainly in what we call the stratiform part of the storm, so where there are no significant vertical motion. But also we are trying to see if you can say something about updraft and downdraft vertical velocities in the parts where this will be dominating the signal. Because of course the signal, since the signal is a line of sight, you see the equation, of course it comes, I mean, it's a combination of the horizontal winds and the vertical winds and the sedimentation velocity of the particles via trigonometry, essentially. And then we also, of course, we will produce also cloud and precipitation products. If you know previous mission like CloudSat and FCare itself, they have basically 94 gigahertz. And basically, we will derive very similar products to those previous missions. But also, the surface backscattering, the Doppler coming from the surface and the emissivity will enable also some secondary products which are related to the surface. And in particular, we'll be able to say something about sea ice and snow over land, and also ocean surface current. And this will be the aspect that Luis will cover in a few minutes. Okay, now this level 2 products, basically that are produced ray by ray, can be used actually to reconstruct the three-dimensional products on the full swath, the 800 kilometers swath. The problem, of course, is that there are gaps to be filled. So we need to essentially come out with some machine learning or three-dimensional reconstruction things. And for instance, we are thinking about producing 2 main products here. So will be the three-dimensional ice mass field. So we look at really how the ice is distributed vertically in these storms. But also we should be able, and we have already tested that we will be able to retrieve the horizontal wind vectors in the stratiform regions. And this is because thanks to the scanning pattern, we have several points within the swath where we have actually what we call 2 independent looks. 2 independent looks, of course, will allow us to retrieve the full vector wind. But we will also go further, okay, and we will try, especially capitalizing on the fusion with the global observing system, but in particular with the geostationary observation that have a very short revisit time. We try to shift towards what we call a Lagrangian or a storm-centric approach. And somehow WIVERN will be used as a calibrator for the geostationary observation. So we will be able to enhance product like the 3D ice product, but instead of having only at the instant of the overpass of WIVERN, we try to extend temporally using the geo, but also the convective stratum of separation, the upper level winds, for instance, that are very well retrieved at the moment by geostationary. We'll see if we can use WIVERN as a calibrator. And other product like precipitation could also benefit from that. Yes, and of course, what we want to do is to provide information about the storm tracking and the life cycle. This, of course, is to address mainly our first two science objectives that I mentioned a few minutes ago. Now, to illustrate a little bit better this storm-centric approach, I'll give you another example, also based on Milton. And let's see if I can start the video here. So Milton actually took 5 days to go from tropical storm to category 5 and then make landfall in Florida. You can see here the evolution of the hurricane in GOES infrared images. And you see the hurricane going through the Gulf of Mexico. So the color of the eye, as you see, are modulated by the storm intensity with the color table on the right. And the video is pausing every time WIVERN passes in the area, showing also the WIVERN sampling acquisition. So you see that there are 10 overpasses in the area. But out of these 10 overpasses, you see that there are only 5 that are good in terms of hurricane sampling. What do we mean? We mean that in that case, the ground track of the satellite is actually passing within 400 kilometers from the epicenter of the hurricane. And these are, you see, the square indicates the closest position of the ground track, and the diamond indicates the position of the center of the hurricane at that instant. I want also to draw your attention particularly to 2 descending overpasses, number 2 and number 3, which are actually separated only by 24 hours. And the characteristics, very interesting characteristics, is they are across the rapid intensification period that for Milton, you see, in less than 24 hours, Milton went from category 1 to category 5. And this is one of the things that hurricane people, they don't understand very well. And I think it will be interesting to use WIVERN data to better understand this kind of phenomena. Now, what we can do within a single overpass, a single snapshot, as I said, we can use the scanning and the dual look to reconstruct the vector wind. So we start from the level 2, the horizontal line of sight wind, and then we use the multiple looks to retrieve the wind. And this is what we can actually do. You see, this is the acquisition of the reflectivity, the retrieved wind. Remember that we can only retrieve winds where we have good targets with good reflectivity, with good signal, with good SNR. This is the retrieved wind, and this is the reference. Okay, and you see, as before, I go from 1 kilometer upwards, 3, 5, 7, 11, and 14. So essentially, you can clearly see, when you go from 1 to 14, you can clearly see that you pass from, sorry, let me go back 1 second. Yes, you can clearly see that you go from the cyclonic circulation close to the surface. And then as you go up, you move above the freezing level, you enter at a certain point the anvil, and you see actually the upper level divergence at 15 kilometers. Okay, so basically this will somehow demonstrate that WIVERN will provide an unparalleled reconstruction of wind vertical structure. In particular, of course, we are very interested having WIVERN at 600-meter vertical resolution, looking at this vertical wind shear And this particularly because we have a very good sensitivity of the ice path, we will be able to actually look very well at this upper level divergence and then the circulation. Now, think about repeating the experience and having the two overpasses that I show within 24 hours. You can actually repeat the retrieval. And here I'm comparing the two overpasses when Milton was category 1 to category 5. And this is essentially, of course, with the sampling of WIVERN, this is what we will see. Again, from 1 to 14 kilometers, contrasting the two situation, hurricane category 1 and category 5. Okay. So two major take-home message here. The fact that we will be able to see, for instance, of course, you need to be a little bit lucky. The movement of the storm has to essentially match with the orbit of the satellite, but we'll be able to see these changes in the internal structure of the storm circulation. Sometimes we refer to metabolism of the storm. And somehow, yes, we will be able maybe to better understand and provide a unique insight in this physical process that underpin the storm evolution, like rapid intensification or rapid decay. Okay, and of course you can put this, instead of having this horizontal slide, you can put that in the vertical cross sections. And again, essentially we will be able to see where the mass of ice is, and somehow we'll be able to understand how things are moving inside the storm. In this case, you see the white arrows are our retrievals, the black arrows are the real winds. Of course, you will not be able to see winds outside in clear sky path, but we'll be able to see the winds where we have a reasonable signal with good SNR. Of course, you may ask if this sampling of Milton was kind of exceptional, was extraordinary. Actually, what we did was a short study where we actually look at all the tracks of tropical cyclones of category 1 and above. And essentially, we computed that we will have a useful overpass of WIVERN every 1.55 days. This means that accounting for essentially the lifetime of such storms, several days and maybe weeks, that with an average of 40 tropical cyclones of category 1 or more per year, we will have basically 300 WIVERN tropical cyclone overpass per year that are useful. And so this will provide, of course, a very good database to understand tropical cyclone. And of course, we can repeat exactly the same experiment with all other different type of storm. So thanks to this very good sampling, this 800 kilometers worth, I think we'll have an exceptional data sets for understanding storms. So I will now leave the floor to Louis, who will discuss a little bit the secondary objectives of the mission associated to the ocean surface characterization. So please, Louise.
Okay, thank you, Alessandro. So where I got involved was the fact that, of course, the main targets of WIVERN are in the atmosphere, but after the radar beam has crossed the atmosphere, it reaches the surface, and so it will also provide measurements of the sigma naught, the backscattering cross section, of the Doppler frequency shift, and also the coherence between the VV and HH returns. So there is a potential to use those ground observables to measure Earth surface properties, such as sea surface current or sea ice properties, and maybe scatterometric sea surface wind, which would be very interesting, especially having the WIVERN observations above, but is probably very challenging because this would require correction of the received power for all the atmosphere above. So that's probably not going to be an easy task. So here I show on the left what 1 day of WIVERN coverage yields, and showing also on the right that we can achieve global coverage in 5 days. Also, so some other MAG members would be able to discuss sea ice properties, but I'm not going to address that question today. Thanks. Okay, so still there are some issues with the ocean surface current measurements. So one point is WIVERN has some very good properties for an ocean radar. So as its aim is to observe atmospheric targets which are fairly faint. The transmit power is very high and the receive sensitivity is very good too. So that gives plenty of space to observe the surface. And probably we can go to quite unusually low SNRs or cross sections if needed. So also, as WIVERN is intended to do Doppler measurements, we know that the pointing knowledge is going to be in the right type of accuracy for ocean current measurements as well. And also the beam diagram is very narrow since we have a 3 meters dish and a 3 millimeter wavelength. So this is quite good too. But there are some other properties which we would call challenges. So that instrument is going to work in W band at moderate medium incidence. And so that means that we're basically in uncharted territory. We have absolutely no heritage on the backscattering cross-section and the wind Doppler GMFs. So that's a completely open field. And there is another thing is to achieve its atmospheric observations goal. WIVERN uses a really specific scheme known as polarization diversity pulse pair, in which the Doppler phase is estimated using pairs of pulses, and one of which is transmitted and received in horizontal polarization, and the following one is transmitted and received in vertical polarization. So this is well established in atmospheric sciences, but we have no idea what the coherence between those two signals is going to be over the ocean surface, and it's for the time being not clear in what range of environmental conditions we will be able to get a good signal. So overall, we can say that our science, SRL is quite low, and to the point that we can't actually say for the time being how many useful data we will get for the ocean products. Next, please, Alessandro. Okay. Still, we had the opportunity to have a proof of concept campaign that was performed over the Bay of Fundy in October 2024, using an instrument, a W-band instrument that was actually implementing that polarization diversity pulse pair scheme I was mentioning. And so those two maps show on the left, we have the track and conditions for the morning flight, the morning of October the 21st. And on the right, we have the conditions for the afternoon flight. So the data that are shown here are from the NOAA Gulf of Maine operational forecast system. Basically running a ROMS model over the area. And so this is a place where we know that currents are dominantly tidal. And so we see that on the left, it's low tide. We have a 5 to 6 meters per second wind from the west and roughly 1 meters per second ebb flow current. And in the afternoon, we have similar winds, but the current is now going to the northeast with roughly the same magnitude. Next, please, Alessandro. So here on those two plots on the left, the ones with green dots all over the place, we show the Doppler frequency shift that we measured as a function of line of sight azimuth. And so we had that daisy pattern flight. And so we can see that as we are looking in varying directions, we have a Doppler shift that has a sinusoidal variation with azimuth. This is after correction for wind Doppler, and that was done using the Ka band GMF that was proposed by Rodriguez et al. In 2018. This was a Ka band GMF, but we had nothing else to use, so that's the one we used. And of course, there is a strong scatter in the points, but that's due to the waves' orbital velocities because the field of view is very small. And so if we go to the rightmost plot, we see that we have, yes, so the model, the Gulf of Maine operational forecast system arrows are the cyan ones. And so we see that on the morning, the current is going to the left, to the southwest, and the radar estimates of current we get are those arrows, various arrows for the different parameterization, for the different polarizations. And we see that between the morning flight and the afternoon flight, the current reversal is very well retrieved by the radar measurements. We see also that doing the PDPP scheme gives the green and black arrows, which are fairly similar to the arrows, the red and blue arrows we get using normal copolarized Doppler measurements. So we see that this confirms that W-band PDPP might be a workable approach to observe ocean currents, at least in these environmental conditions, but which are fairly common, you know, like 6 to 7 meters per second is something that is quite frequently observed over the world ocean. So that means that we don't know yet how far we can go from these conditions, but WIVERN will probably give something useful, at least in these conditions. So what are the next steps for us? Next steps would be to design and deploy a field deployable instrument to be able to collect data in a wide range of environmental conditions, to be able to extend this and know in what conditions WIVERN would actually provide data. And then using this, implement L1 and L2 simulators. So the L1 simulator would be used to evaluate the radar signal statistical properties, and the L2 simulators would give access to estimates of the data return, like what percentage of the time would the NRCS be sufficient and the atmospheric attenuation be low enough for WIVERN to work well, and yes, have ideas of the L2 products, noise properties, uncertainties, estimate that the potential for scatterometric 10 meter height wind products and things of that kind. And our objective is to catch up with the primary objectives in terms of SRL by the end of the phase B studies. I think I'm done, Alessandro. This is back to you again.
Yeah, thank you very much. So let me just draw some final conclusions and remarks. So I have 4 bullet points. The first one is that WIVERN is for sure is a groundbreaking concept and will be the first mission to provide measurements, 3-dimensional measurements of the distribution of mass and winds inside clouds over multiple scales at 1 kilometer footprint and across essentially 800 kilometers worth. And second, the simultaneous measurements of storm dynamics, cloud and precipitation contents will advance for sure our understanding of storms and actually help also to constrain cloud feedback processes. I didn't show example, but WIVERN will also generate data to benchmark kilometer scale global models. And this is because it will do the same thing that healthcare and CloudSat have done, but with much faster sampling rate, essentially. And also we provide data to improve weather predictions. At the moment, we have already seen that there is a lot of impact assimilating the winds. At the moment, they are also, ECMWF and Meteo France, they are also looking at the impact of assimilating reflectivities. They are doing some exercise with the healthcare. And also data to support the science-based decision making for the benefit of all. And then the fact that we have this Doppler radar with the radiometric mode also, instead of observing, not only will observe the atmosphere, but also observe the surface. And we will have, therefore, coincident observations of the atmospheric wind profiles and the ocean surface current. Hopefully, we will have to work on that. This aspect is low SRL, but it's in the pipeline. And hopefully this will give us some insight into air and sea interaction processes. So of course, the launch of the mission is expected for 2034 if everything goes as planned. So we have at least 8 years to work to get ready, to consolidate the science, and to build an interdisciplinary community around the missions. And we are particularly happy to present WIVERN in this seminar series to start actually exploring with your community the potential of WIVERN observation for providing insight, in fact, into these air-sea interaction processes in the years to come. And I thank you for your attention. If you want more information, you can go to this website where there are a lot of papers about the mission. And on the other hand, at this website, there is actually the report for mission selection, this 300 pages report that we wrote before the user consultation meeting where they took the final decision. Actually, you can also see the 2-hour videos where we presented the mission. Thank you for your attention.
Thank you very much for the nice presentation. And I think we can open the floor for questions. Maybe while people line up. So if anyone, okay, we have one. So please add.
Okay, yes, you can hear me?
Yes.
Okay,
Yes.
very good. Very nice talk, Louis and Alessandro. Also very much close to missions I'm involved in, actually, on the Harmony clouds and surface winds and the DOPSCA and the SCA. And so I think it's very interesting that all these may come together at some point, if Aeolus 2 even. So that would be really great, of course. Yeah, I had one comment on airplanes, because they measure in clouds, of course, and we have quite a dense network in Europe from Mode S. We actually process them at KNMI. And yeah, of course, they measure both in clear air and in clouds. So do you plan to use these as a reference for your mission?
For validation, you mean?
Yes,
of course,
yes.
we can use for validation, yes. Of course, the problem of that measurement, as you know, they correspond, typically they do the profile close to the airport, and of course they then they take data at the cruise level only along the path of the aircraft, right? So of course, but of course we will use that together with of course the radiosondes, and also of course we'll use a lot of this Doppler radar from the ground, which also will provide as a reference, I mean, validation for the winds. Yes, this will be the yes. But for sure, asking, well, I think we are, I mean, for sure we are complementary, because typically aircraft also tends to avoid, of course, storms by definition. Of course, they will go into clouds, so they will have plenty of data inside clouds, but maybe not in the most violent part of the storms. And the important thing is that we have done I mean, Meteo France, Sasso et al., they have done a study looking at the situation that we will have the observing system for winds in mid-2030. They have considered, in fact, the synergy with Aeolus 2, and they actually proven that the two observing systems, they are very complementary, because of course Aeolus 2 is very strong in clear air, the top of clouds, and WIVERN on the other hand is very strong inside clouds, and has a much better sampling because of this scanning pattern. So we have seen that indeed the impact on data simulation is huge, and the two are complementary. So the Aeolus is not canceling the other or vice versa. So they are indeed very complementary, just because, of course, the physics of the two instruments is completely different. One is a LiDAR and the other one is a radar. So we know that of course, the response is completely different depending on the target.
Yes, for sure. That's appreciated. I think also with machine learning approaches, you may be better to assimilate dynamic situations, which is a bit problematic for the classical systems, yes, that we have that we use for Aeolus. But I think for your system, as time proceeds, we may go to these Doppler approaches, and I think the data is very well suited for this purpose.
In fact, we have done so far the study with standard data simulation, but as you have seen in the third objectives, now we are, of course, we'll have AI as well, because it's catching up, and probably in 10 years' time, who knows? But for sure, this data will be very valuable, because AI needs data, and these data are unique. So we are confident that this will be very useful.
Yeah, sure. I'm also, yes. Yeah. Okay, let's leave it there, and others can ask questions, I guess.
Thank you. Yes, we have Sarah. Please, Sarah.
Yeah, really interesting. I'm wondering, but for these different conical scans, there's spacing between them. What is that spacing? And how does that compare with the scale of
it depends.
Updrafts and things in storms that you're looking at?
Yes. Okay, so let me see if I can share 1 second again. So the spacing depends on, let me just show you yeah, it is. So you see, this is the scanning, right? You see clearly the spacing is very different if you are at the center of the swath or if you are at the side of the swath, at the edges of the swath. At the edges, we have very good coverage. At the center depends on the height where you are, and now actually we are still studying the repetition frequency. I mean, the velocity now industry, they are asking to slow down a little bit the antenna. So there can be gaps of 10 kilometers, 10, 15 kilometers in the worst case scenario at the center of the swath. So indeed, you know, we need to fill in the gaps, which of course will be very, well, easy. Will be easy in conditions where things are, you know, for variables. So like winds in stratiform regions, which have scales, I mean, correlation lengths of several tens of kilometers. Of course, inside convection, we may actually miss a convective tower because of these big gaps. But okay, this is something we are trying to, of course, we are developing now this level 2C algorithm, because this is the product on this world we call 2C, via this essentially machine learning or three-dimensional interpolation and so on and so forth. But you see, the point is that also at the center of the swath, right, you will basically will only see the components of the wind along the direction of the flight of the satellite. On the side, as you go to the side, you see that you have these two independent looks, and you will be able essentially to retrieve the wind. So essentially, let's say the quality of the retrieved fields will depend a little bit on the distance from the center of the swath.
Have you defined a performance swath or a vector swath versus a non-vector portion of the swath? Do you have scales for those?
Scales for, sorry, for...
So the center of the swath, you're getting one component of the wind, and
the first 100 kilometers are the most critical. The first 100 plus minus 100 components from the center of the swath are the most critical.
And then the 300 beyond that, you have enough information to extract a vector.
Yes.
What are the near real-time requirements?
Okay, near real-time requirements are getting down, if I remember well, 95% of the data within 2 hours or 3 hours. I don't remember whether 2 or 3 hours. I think 2 hours. 90% of the data within 2 hours. So the focus is for sure to be able to provide. I mean, this is one of the main goal of the mission, of course, is to get the data for ECMWF, Meteo France, and the data. I mean, NWP centers for sure. So we have this requirement now. I can dig out exactly the percentage and the hour, but if I remember correctly, is maybe more than 95 within 2 hours.
Thanks.
Thank you. I also had a question if no one else wants to ask. And so you nicely showed us an example of strong convection, like large systems, a tropical cyclone. So the data will be very valuable in this case. So somehow related to the previous question, I was curious to know if you tested conditions where you have smaller scale structures and like low clouds. So for instance, you were mentioning trade winds will also be another region. So how sensitive will the instrument be to like smaller scale and like weak, like shallow convection and these sorts of weaker signals?
Okay, this is what we intend to do more in depth in this B1 phase, B1 and B2 phase. What we have done for cumulus and stratocumulus is run simulations, but mainly to look at the cloud and precipitation products. Because in that case, we have this radiometric mode, which is very interesting because it's the first radiometer, let's say at 94 gigahertz with a sub-kilometer footprint. So essentially the brightness temperature over the ocean, typically they start very cold, and as you put liquid, they start warming up. And this warming up of the brightness temperature, we know is proportional to the liquid water path. So we'll be able to do this liquid water path for cumulus clouds at very high resolution. This will be very unprecedented. But for the circulation and for the winds, this is one of the topics we are going to do in this B1 phase with colleagues, in particular colleagues from Max Planck Institute, Kathy Ogenegger. They are running a lot of these icon models, so we will try to do these tests. We simulate WIVERN flying over this system and see what we can get. For sure it's challenging. For sure it's challenging. Will be challenging. Shallow stuff will be challenging. I didn't mention one thing is that because over the ocean, because we are looking at slant angles, we know that the sigma naught will be strongly reduced. So we know that the return from the ocean will be strongly reduced compared to Nadir radar. I mean, we have a long experience with clouds in healthcare now. So what we expect actually is over ocean, we'll be able to see, despite the fact that we are looking slant, because the sigma naught is reduced, we think we will be able to see below 1 kilometer hydrometeors and you know, rain and drizzle and those kind of things. But yes, this is part of the as I said, part of the work we are doing we are planning to do now in phase B1.
Thank you. So is there anyone else who wants to ask a question? Otherwise, I think we can thank again our speakers.
Thank you very much for the opportunity.
Thank you very much to you.
We are happy to answer additional question. You have my email, Agostino. You can forward to me or to Louis additional questions, and we are really interested in starting possible collaboration if anyone wants to collaborate on the topics. As I said, some of the things will come a little bit as serendipitous, let's say. We started also, just to mention, when we were in the first selection, so it was in phase 0, we were really targeting as main goal of the mission was assimilation, and improving numerical, whatever. We are trying to add more science to the mission, and so everything could help to make a great mission.
Right. Thanks. So add if you want a very short
Yes,
comment,
just
and then we
a
close.
very short question. Because I'm interested in the local solar time of your mission. Do you fly sun synchronous?
Yes.
At what time?
6.
Oh, 6. Okay, that's very nice.
Okay.
So we have also the Chinese spectrometers flying at 6. So we.
So this is we have two things that we need to assess now as a first thing in phase B1. One is the rotation of speed of the antenna. The industry, they are already asking to reduce the budget and the price to slow down a little bit the antenna from 12 to 8.
Yeah.
The second thing we may reconsider is the local time. Remy Rocca from CNRS, he wants to really understand if we are sampling which kind of life stage of the storms and so on and so forth to see if we have too large gaps or whatever. So we are reconsidering a little bit that. I'm not so sure how much margin we have from industry to change it, because that orbit was selected in first place to minimize essentially distortion of the antenna, which of course is very relevant for what Luis mentioned, which is the mispointing. So to do Doppler properly, you need to have the mispointing absolutely under control, and therefore you want to minimize the thermoelastic effects on the antenna. So that was the main reason actually why we selected in first place. Actually, was something the industry saying you have to go, and so it was a kind of prescription. Now maybe they allow a little bit of margin, but I think it's a good. Any suggestion on that for synergy with other instruments that could be useful?
What is the local time for Aeolus?
That's very nice. For
the LiDAR system, Aeolus, what's the local time?
Also, Aeolus, we fly at dawn dusk at 6.
Ah.
Yeah. If we fly Aeolus 2, it will be at 6.
Or kind of, yes.
Yeah, so that would be very nice if we could have them together, of course.
Yes, but it will not be, it will be a different, so we are at different heights.
Yes, so the phasing will change in the 6 o'clock orbit, but there will be times when they overlap and times when they will not overlap. So I think it will be generally quite useful if you look at processes.
Yes, the other thing I can tell you, we are already discussing with other missions, particularly we have already discussed with the Arctic weather satellite, so what is called now the Sterna constellation. They may consider to fly a satellite with us in companion. So
also very nice. You have the Chinese spectrometers that also fly at 6 in the morning, so you also have surface truths, let's say.
Okay, good.
And we process them at KNMI.
Okay, good.
Yeah.
All right. I think time is over. So thank you very much for the very nice presentation and for joining the discussion. So I think we have a meeting next week, right?
No, I think we don't yet have a speaker, but we're talking to some people. So stay tuned.
Right. Yeah. Yes.
And definitely the week after.
All right. Thank you very much.
Thank you.
Thanks.
Bye.
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 Thank you. Bye-bye.